This is feedback and some answers for homework number 6, which is due, turned in, uploaded to Blackboard, scanned on Wednesday by 10:30. Also, we're having a quiz on this Wednesday, over this homework. So look for an look for a Blackboard announcement on that and the quiz. All right, problem number 1. You're calculating CL beta of the vertical tail. We have a formula for that from our textbook and from our notes. So really you just substitute the numbers in and you should get this value here. So this is the roll due to side slip of the vertical tail. So the problem says compare with the answer or the number that's given in Roskin for this same airplane. Number here compared to this, and see if you can come up with a reason why there's such a big difference. The answer is underneath this Wooshock logo, or sorry, the WSU logo. Whenever you see that, it means I've blanked out some of the solutions that you need to fill in your homework. All right, problem number 2, we have a side velocity of 50 and a total velocity of 250, so you need to calculate beta. From that vector diagram, you should get 0.20 radians. Then it's just a matter of substituting that into the two equations and solving. You should get an aileron of about 30 degrees and a rudder of about 30 degrees, both near the limits, if not past the limits, of what you might be able to achieve on this airplane. So that says flying in a steady state side slip of 11 degrees, that's a big side slip. Okay, that was problem 2. Problem 3a, you're taking the inverse Laplace transform of this function, do partial fraction expansion, which means you need to find these coefficients for the expansion into the 3 factors. So here's the answers for those, and make sure you show your work, especially the inverse Laplace transform that's underneath the WSU logo down here. All right, part B, find the inverse Laplace of this. Because it's got this second order factor, you have to expand into s plus 1 and s plus 1 squared and s plus 3. Don't know if you learned this in differential equations, but there's a trick to finding this coefficient using the multiplication technique. Because if you multiply by s plus 1 squared, you can get a2. Multiply by s plus 1 squared and evaluate at the pole. If you multiply by s plus 3 and evaluate at minus 3, you can get the coefficient there. But if you multiply by just s plus 1 across both sides, you're still going to have an s plus 1 in the denominator of a2, and you're going to be stuck because when you plug in minus 1, it's going to blow up and go to infinity. So one way to do that is to multiply by s plus 1 squared and then take the derivative, which knocks out one of the s plus 1's, and then you can evaluate for the a1. A better way to solve this problem is the technique you probably learned in differential equations, where you simply multiply both sides by the entire denominator, and then you equate equal powers of s. So this is s to the 0 here, s to the 1, and s to the second power, excuse me. So then you solve those 3 equations for the 3 unknowns, which takes a little bit of work, but it's more straightforward. Once you get the numbers for a1, a2, and k, then simply inverse Laplace. Okay, for a, you're solving this differential equation. So you simply take the Laplace of both sides. So the second derivative turns into an s squared plus the initial condition terms. The first derivative turns into an s times f of s. Initial condition terms. The f turns into f in the Laplace domain. And then the right side, look that up. You just look up the e to the minus 2 in the tables, and you get this. You ignore this step function that's listed there. That just turns this thing on at time t equals 0. But that's how Laplace works anyway. Alright, so then you solve for f. And then you do the partial fraction expansion. Here's the factors you should get. Once you work through this, you can do this one with just the standard technique or multiplying both sides by the entire thing. And then the rest is left up to you to solve the inverse Laplace transform of that. Notice that it's important to put in the initial conditions here and here and here when you solve this. In a general equation, these initial conditions will not always be 0. And then you can finish this off yourself. I'm going to leave 4.4b for you guys to try for extra credit. Give it a shot. It's 2 equations. You just Laplace both equations. In the Laplace domain, you solve for the 2 Laplace transform function unknowns, and then you do an inverse Laplace transform.